Can you hear me? Hello.
Yes, sir.
Okay. So in the last class, we were discussing about electromagnetic field tensor. So we introduced a new mathematical object which we have named now electromagnetic field tensor. So electromagnetic field tensor is a mathematical object which completely describes the electromagnetic field in space-time. And if you think in terms of this object, you don't need to worry about electric field and magnetic field separately, because they are nothing but the components of this tensor. And all that you need to care about is the transformation of this object, because once you know how this tensor transform between different inertial frame, you can figure out how the electric field and magnetic field will look like in two different inertial frame. So this tensor, which we defined electromagnetic field tensor, it's a tensor of rank 2, and this is an antisymmetric tensor, f mu nu, or fij, whatever you want to use. It has two indices, and these are the space-time components, or time-space component, whatever you like to call it, x by c with a minus sign. And then you have space components, 0, this is bz. There are other ways to write this tensor, which, so but I think, I mean, you stick to one particular way of writing it, otherwise you may, I mean you may confuse it. I mean, there are multiple ways to write this electromagnetic field tensor, but you don't need to worry about that, because ultimately it's representing the same thing. Okay, so if you go to Jackson's book, I mean, that doesn't use c, or some other books, I mean, this could be plus, this could be minus, this could be plus. So initially things may look like they're different, but they're not different, because if you use the equations, they will yield to same result. And this is y, because it's antisymmetric, this will be bx minus bx, and then this will be 0. Diagonal components will be always 0, because this is an antisymmetric tensor. So this object, it transform. So we know that how it transform under Lorentz transformation, right? So we need to just and we have also seen by transforming this object across two different inertial frame, that the transformation of the individual components, the 6 distinct components of this tensor, exactly look like the transformation of electric and magnetic field that we have seen from the transformation of Lorentz force, right? And since this is a contravariant tensor, so we also need to know how the covariant components of this tensor look like, right? কারো একটা মাইক্রোফোন মনে হয় অন আছে, ও অফ করবে, নয়েজ আসছে খুব। So the covariant field tensor, I mean, if we want to calculate the covariant component, the covariant field tensor, that is, if we want to know what is f mu nu, we need to use the metric tensor. I discussed about this, I think, in the last part of my previous class. So if you want to calculate f mu nu from f mu nu, you have to use the metric tensor. So f mu nu will be metric tensor g mu alpha, f, I think, yeah, mu alpha beta, and this will be g nu beta, right? And what is the g mu nu in our case? G mu nu in our case, the kind of signature that I chose for the Minkowski metric, it is 1 0 0 0, and then 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. There is another way of choosing the signature, where you put a plus, minus 1 here, and plus plus plus, but that will not make any difference. I mean, you can try, you can check it. So f mu nu is this one, and if I use this, let us do it. It's a simple exercise. Let me put it 1 0 0 minus 1 0 0 0 0, and then this matrix 0 ex by c, ey by c, ez by c, minus of ex by c, and minus ez by c, 0 dz minus by, and then another 1 0 0 0. So all that you need to do is the simple matrix multiplication, and if you do that, okay, okay, let us do it. It's 1 0 0 0. Okay, let us do the multiplication. So this will be 0, this will be minus x by c, this will be minus ey by c, yes, minus, yeah, this will be minus z by c, this will be row column, right, minus x by c, this will be 0, this will be minus bz, this will be by, this will be minus ui by c, bz 0 minus bx, this will be minus ez by c, minus ez by c, this will be minus by, this will be bx, this will be 0. Okay, so another step, and if you do this, okay, this will be 0 minus ex by c minus ey by c minus ez by c, this line will be x by c, this will be 0 bz minus by, ey by c, minus bz 0 bx, ez by c, by minus bx 0. So if you look at these different components of f mu nu, what you will note that you see the space components, they are same. I mean, they're exactly same. You see bz, this is bz minus by, this is bz minus by, and so on. So space component, they remain unaltered. I mean, there is no change in their sign, and only the space-time components. If you look at these two space-time components, this one, this is time component, and these are also space-time components. They switch sign. You see, ex by c becomes minus ex by c, ey c becomes minus ey by c, ez by c becomes minus ez by c, and similarly the minus signs becomes plus here. So you don't need to actually do this multiplication each time you need to use f mu nu. Just remember that just like a 4 vector, when I have a 4 vector and I want to find its covariant components, we just switch the sign of the spatial components, right? Because we know that if you multiply with this vector with a metric tensor, you can obtain the covariant component. Similarly, you can just remember that given a f mu nu, if you want to have the covariant component of the same tensor, you just have to switch the sign of the space-time components and keep the other things unaltered. So that will give you the covariant components of any such tensor, right? Of course, you can also try by switching the signs. You can check it yourself. I mean, it will give you the same thing. Fine. And similarly, we have another tensor that we defined in the previous class, which we call dual tensor. Again, I mean, it's not a new tensor, as I told you. It's just the same tensor with a different I mean notation. You just switch. You just switch the sign of all e by c replaced by b and b by minus e by c. That will give you a tensor called dual tensor. But again, physically, I mean, it's just a different representation, and it doesn't contain any extra information. And again, you can calculate g mu nu in the same way. right? So I'm not writing that. Once you write g mu nu, just switch the sign of the space-time component. That will give you g mu nu. And by combining this f mu nu and g mu nu, because we know that the dot product of two four vectors is a Lorentz invariant that we have learned earlier. Similarly, and 4 vector is nothing but a tensor of rank 1. So I mean, mathematically speaking, I mean, they are just different tensor of different rank, right? So it's not like it just hold for tensor of rank 1 and it will not hold for tensor of rank 2. It will hold for all the tensors. So this is a tensor of rank 2, and if we take a dot product of the tensor, say if I consider f mu nu f mu nu, or say f mu nu g mu nu, or say g mu nu g mu nu, what are the products, right? They must be Lorentz invariant. So we shall calculate those. That's straightforward once you remember f mu nu and g mu nu. So yeah, let us do that first. Let us calculate f mu nu f mu nu. So what is that? If we calculate f mu nu, right? Let us calculate this. We want to calculate f mu nu, that is equal to. So basically you just have to, since Einstein convention, basically you repeat everything. You can keep this is fixed, mu is 0, okay, f 0 0, and then I am changing mu, f mu is 0 0, yeah, and then f mu is fixed 0 1, and mu is changing f 0 1, again mu is fixed f 0 2, mu is changing f 0 2, f 0 3, f03, then I will change again mu, f10, f10, f11, f11 plus f12, f12, 13, 13 plus f20, 20, 21, 20, 22, 21, yeah, 2 fixed, right? Yeah, f22 plus f23, f23 plus 30, 31, 32. So altogether we have 16 terms. If 32, yeah, 33, f33, yeah. And we know the individual components, right? Because you know f00 is 0, f01 is ex by c, f02 is ey by c, f03 is z by c, right? Similarly, if 10 is minus ex by c, and so on. So we just have to put the values here. So let us do that. If this first term is 0, second term is because this is f01, this is f01, and it's an anti-symmetric tensor, so this is plus, this will be minus. So ex by c and minus ex by c. Similarly, f02 is ui by c, plus sign with a minus sign. And you check, if I make the top row negative and the first column positive, that will also not make any difference, because plus minus or minus plus, that will be minus in anyway. ui by c plus third is ez by c into minus ez by c. So all these are negative. Yeah, plus, yeah. And then I have, what is that? f10. Where is that? Wait a minute, where is that? Where is the pen? ah, Plus ez by c plus minus ex by c. This one is minus ex by c. F10 is minus ex by c, and f10, yeah, that is again minus ex by c, right? Minus plus plus, right? Yeah, f10, yeah, this is again negative x by c, and plus 0 plus bz square plus bz and bz square plus by square plus minus uy by c plus uy by c plus bz square plus 0 plus bx squared plus minus z by c plus by square plus bx square. So if you combine them together, you will see that the each term appears twice. So twice b square plus by square plus bz square, that is b square minus e square by c square. Now we have already seen this, right, before, when you, because when we calculated this ex, ey, ez, bx, by, bz into different frame, and then just combine them, we saw that e square minus c square b square is a Lorentz invariant, and that is the same statement here, because you see f mu nu is nothing but with a minus sign. Okay, of course, e square minus b square c square. If you calculate g mu, I'm not repeating this because that's a trivial exercise. Everybody you can do this g mu. If you calculate this in the same way, just put the different components, multiply them, simplify it. That will give you twice e square by c square minus b square. Again, that's a trivial exercise, so I leave it for you. Just check this. The g mu will be twice e square by c square, and both of them just are just pointing towards the fact that this should be Lorentz invariant. E square minus c square b square, this should be Lorentz invariant. I'm talking about this magnitude of this quantity. It should be Lorentz invariant. Similarly, you can also calculate f mu nu g mu nu again, because it just is a identical exercise. You don't need to worry about. You just have to calculate again f00 in place of f. You write g00 and then f01. So I am not doing it. You just do it, right? Plus dot dot dot, because you know the form of f0, f mu nu and g mu nu. If you put the values of all the terms, you will finally come up with this minus of 2 by c e dot b. Both the terms will give right. I mean, if you combine all the terms, you will see something like this. I think, yeah, it's 4. I think, yeah, 4, not 2. Minus 4 by c e dot b. And you see again, I mean, other than this constant factor over there, minus 4 by c, what it is telling you that the Lorentz invariant of the electromagnetic field is E dot B, which you have seen earlier. But not, this time we are seeing it from a different perspective. We are not considering E and B as separate entity. We are considering the electromagnetic field tensor F mu nu is the single most important quantity representing the electromagnetic field, and calculating the Lorentz invariant from the dot product of this quantity with itself. The first one is obtained by taking dot product of the f mu nu with itself, and the second one is obtained by taking dot product of f mu nu with the dual tone, with its dual tone tensor g mu nu. So both these quantities are expected to be Lorentz invariant, which we have already learned from some other discussion. Okay, but what is the use of this f mu nu? Why should we? I mean, what is the advantage of using it? I mean, first of all, if till now, from the, I mean, for the beginning of the study of electricity and magnetism, we have learned that electric field is a vector which has 3 components. Magnetic field and another vector with 3 components, and depending on the source of electric field and magnetic field, we can have the different components can have different values. But when you come into the realm of relativity, special relativity, where you are working in 3 space with the 3 space dimension and 1 time dimension, you have to drop those notions, right? Because here we know that those notions are basically artificial, because that was convenient to us, and since you do not face any problem there while dealing with such a problem in electrostatics and magnetostatics, so you did not bother about that. But this time you are not only discussing about electrostatics or magnetostatics. Right now we are discussing about electrodynamics, and relativistic, particularly relativistic electrodynamics, where we know that the space-time is 4-dimensional. So there is no way to escape this, because all these things that we know, position vector, velocity, momentum, these are 4-dimensional quantity. We artificially break them up and see them as separate things, like energy and momentum. They are nothing but the different components of the same 4 vector. In the same way, in the same spirit, the electromagnetic field tensor is telling us that electric field and magnetic field, they are not separate entity. They are components of a single mathematical object, right? And once you learn how to transform that tensor from one inertial frame to other, you can actually figure out what should be the value of its components in different inertial frame. So you don't need to think about electric field and magnetic field separately at all. right? You can forget about the electric field. What is electric field? What is magnetic field? You just ask what is the form of F mu nu. Give me the form of F mu nu. I will tell you what are the components in some other frame. So that's the advantage of it. So first of all, I will just show you one example, that is one familiar example, because I have already discussed that example in, I think, a few classes back, where I showed you how to transform the electric field and magnetic field for say a line charge density. You may remember this, I have discussed, I think 2 or 3 class back, where I discussed how the line charge density, which is lying along the x-axis in the laboratory frame, transform another frame which is moving with respect to the lab frame along some direction, right? So we shall do the same problem here, right? But this time using this electromagnetic field tensor, not thinking them the individual components like electric field and magnetic field as separate objects. So let us do that. So I think all of you are familiar with that problem, so I'm not repeating that problem. Maybe I can just tell in a few words. So the problem was the following. So you have as a laboratory frame where okay, let me draw the laboratory frame where you have a wire which is not carrying any current. It's a wire. Okay, it's a charged wire. I told you this is a charged wire. Okay, positively or negatively doesn't matter. Charged wire, and line charge density was given. So lambda is the line charge density. Line charge density. And we considered another frame which is moving along the x-axis. Of course, you can take any other frame. I will also give another example. So this is, suppose this is lab frame S frame, and we have another frame S prime frame moving along the x-axis with velocity v. So let us call this x prime, y prime, and z prime. And what we are interested is about the electric field and magnetic field. But again, what is electric field and what is magnetic field? We have seen that electric field and magnetic field in one frame they may have a non-zero component, another frame one of them may vanish, right? That we have seen because they get mixed up, right? Because they are the components of the same quantity, right? So it is not like the magnetic field is a separate thing and electric field is a separate thing. They are components of the same entity. Just because you are transforming from one frame to other, which is nothing but rotation, right? I told you Lorentz transformation is nothing but a rotation in hyperbolic space. The components may change, right? The components may change, but the things which remains invariant is the length of the 4 vector. Although this time the dot product of the 4 tensor with itself, that should remain invariant. That's the requirement. Other than that, you don't need to think anything. I mean, the components may be different in different frames. Of course, there are certain invariants which has to be obeyed. As we have seen that F mu nu is E square minus C square B square. That has to be remain invariant. That's one requirement of relativity, right? We are not imposing it. And then the second requirement is E dot B must be same in all inertial frame, right? Accordingly, the components will transform. So obviously, so we have to first write down the components of F mu nu in this frame or in that frame. So in this case, we know the F mu nu in this frame, right? So what is the F mu nu in this frame? So I think from the previous class, I am not repeating the calculation once again, because in that case we calculated electric field, right? So although physically electric field, what is the electric field? Lambda divided by twice pi epsilon 0 y square. There is no electric field along the x-axis, right? We have discussed this, and the 3 components 0, y, and z, right? These are the electric field, and there is no magnetic field, b is 0, right? So we know all the components. Ex is this, I mean 0, ey is lambda. You can also call this lambda 0. Maybe that will be easier. Lambda 0 into 0, y, and z. Let us call this quantity lambda 0. Okay, this entire thing is lambda 0. That will be easier to write, right? So the x component is 0, y component is lambda 0 y, z component is lambda 0 z, and b, that means we know the components explicitly. So ex is 0, ey is lambda 0 y, ez is lambda 0 z, and then bx is 0, by is 0, bz is 0. So in principle, we know all the components of the field tensor, right? So that is the thing that you have to write down for one time, and then you can forget about the rest, right? You can go to any other frame and calculate the things, because of course you have to calculate it for the, I mean, for the sake of writing the f mu nu. Unless you know f mu nu, how do you transform it? So that's the requirement. So at least for one time in one frame, you have to write down f mu nu. So in this case, what is the form of f mu nu? F mu nu in the laboratory frame is so this is 0, of course 0. This is ey component, right? So ey is again, lambda 0 y. Maybe I'm not mixing them up. I'm just writing ey. If you want, you can put that ey by c, because that will be easier to remember. This is lambda 0 y by c, lambda 0 z by c, and it's antisymmetric, so it has to be minus ey by c and minus ez by c. You can just write it, I mean, with a confidence, without thinking anything. And we know the magnetic fields are not there, which represents the spatial component. The space-time components are represented by electric field, and the magnetic field is represented by spatial components. Because there are no spatial components, then magnetic field is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So once I know this, my job is done. Right? And in this particular example, I have considered the prime frame to be moving along the x-axis, right? So what is the corresponding Lorentz transformation matrix? If I ask you lambda mu nu, that the usual Lorentz transformation matrix which you have used many times, gamma minus beta gamma 0 0 minus beta gamma gamma 0 0 0 0 1 0 0 0 0 1. Yes, that's all what you need, right? And now we want to calculate this quantity. So basically velocity is along, this is a velocity, this is important, this is moving along the x-axis. Now remember, I mean, as I told you, the same problem can have different forms, so don't get confused. Once you can solve one problem, you can solve the others, right? The wire is lying on this laboratory frame. I can have put this wire in the moving frame as well, right? Then you have to apply the right transformation equation, otherwise you will get wrong result, right? Or the wire may be lying along the y-axis, or say z-axis, or it can make 60-degree angle with the x-axis, right? So all those orientations are possible. Once you understand the idea behind solving this problem, you can solve all those problems. Or the frame is moving, say, along the y-axis or z-axis, or along certain particular direction, right? Say 30-degree, making an angle 30-degree along the x-axis. You should be confident, I mean, about the solving such problems, right? So I'm just giving you one particular example, right? And then we can want to calculate this primed tensor in the moving frame f mu nu prime, which is what? Lambda mu alpha, f alpha beta, and lambda nu beta, right? Alpha beta, it's alpha alpha beta beta. Yeah. So let us write down here for the sake of that will make easy to come multiply gamma minus beta gamma one zero. This one is simple because we have just two non-zero components, ey by c, z by c, 0 0 minus ey by c minus ez by c, 0 0 0 0 0 0 0 0 0, and then we have gamma minus beta gamma 0 0 minus beta gamma gamma 0 0 0 0 1 0 0 0 1. Right. And I think this is quite repetitive. I mean, I'm not going to do matrix multiplication all the time. You can do it yourself. I am just writing the result here. You can check it afterwards. So I'm writing the result here. Just write down the result. If you multiply this matrix with this one, and then finally the product matrix with this one, you will get this one: 0 0 gamma ey by c gamma ez by c. Okay, this will be 0, this will be 0, this will be minus beta gamma ey by c, beta gamma ey by c. This will be minus of beta gamma ez by c, minus beta gamma ez by c. This will be, of course, it is easy to write down these things. Oh, minus gamma. Maybe I can go to the next page. This looks quite clumsy. View new page after. Okay, so what I am doing here, I am writing uh, the product tensor f mu nu prime, which is uh, lambda mu alpha f alpha beta nu beta. Yeah, this, if you carry out that matrix multiplication, finally you will have a matrix of this form: 0 0 gamma ui by c gamma ez by c, then 0 0 minus beta gamma ey by c minus beta gamma ez by c. Then you have minus of, this is of course gamma ey by c, minus of gamma ey by c. This will be minus, so this will be plus beta gamma ey by c. This will be 0, this will be 0. This will be minus of gamma ez by c from antisymmetry. This will be again, this will be minus, so this will be plus, yeah, beta gamma ez by c, because this is 3 zeroth, this is 1 3 3 0 3 1, yeah, and this will be 0, this will be 0. Now you can figure out what are the components of electric field and magnetic field in the prime frame, right? Because you already know, because this is nothing but the, if I write down in terms of this I mean this field tensor which you have defined earlier. So what is the field tensor? You know the different components of the field tensor, right? Let us, if you want to write down, let us write down that here, because these are nothing but 0 ex prime by c prime, the prime frame, ui prime by c, and then ez prime by c, right? And these are minus ex prime by c minus ey prime by c minus ez prime by c, and this will be 0, this should be bz prime, this will be minus by prime, this should be minus bz prime, this would be 0, this should be bx prime, this should be by prime, should be minus of bx prime, this should be 0. So if you compare the different components of the two matrices, you can find out what are the corresponding components of electric field and magnetic field in the prime frame. Because we physically when we deal with a physical problem, we physically understand what are the electric field and magnetic field, but here you are doing it mathematically. You have calculated the electric field and magnetic field in one frame and written down them as the distinct components of the field tensor, and you have now transformed it to another frame and then comparing the individual component to figure out what are the corresponding electric field and magnetic field. So if you do that in this frame, so what you will find, you see there are no first you see this one, the x component is in here 0, right? So I can straight away write here ex prime is 0, right? And what is ey prime? You can see if you compare, it is gamma ey. What is ez prime? That is gamma ez, right? Just compare, I'm just comparing. What is bx prime? Where is bx? Bx is here, you see there is 0, right? So bx prime is 0. What is by prime? Where is by prime? Why is this is by prime, right? That is beta gamma ez by c, you see beta gamma ez by c. What is bz prime? Which one is bz prime? Bz prime is this one, right? This one bz prime, right? Second row, third column, that is minus beta gamma. And these signs are very important. You see, if you do not use the proper sign, the result is wrong, right? Depending, the magnetic field will point towards the negative z axis, right? And the magnitude will be beta factor times Lorentz factors times the electric field component along the y direction divided by c, right? So you should be careful about using proper transformation, then only you will come up with the correct result, right? If you write a plus, then your answer is wrong, right? So fine, so we have already seen this, right? These results were obtained earlier. So I have solved this problem by simply using the transformation of electric field and magnetic field, those equations which we derived from the transformation of Lorentz force or the force, right? and they are identical. So after you learn to use electromagnetic field tensor, you don't need to go back to those equations and use them for solving such problems. It's up to you. Even if you solve this problem by using those things, I do not have any objection. But it is easier and more convenient to use this equation. I mean this transformation. Uh, so E prime will be what? E prime will be gamma lambda. I mean that lambda 0 that we wrote earlier, twice pi epsilon 0 y prime square plus z prime square into 0. You see y prime, and you see we have y prime and z prime, right? Y prime and z prime, right? But y prime and z prime won't change because the frame is moving along the x-axis. So you can simply write this is equal to gamma lambda divided by twice pi epsilon 0 y square plus z square time 0 y and z, right? This is your electric field in the moving frame. And the magnetic field, you remember the magnetic field was 0 in the laboratory frame because the wire is lying in a static way, right? It's just lying on the floor along the x-axis. It should not produce any magnetic field. But in the frame where it is where the wire is no longer static, so electric field, maybe I can write it here. The electric field E prime, we wrote it to be mu lambda twice pi epsilon 0. Y prime and y is same, that's why I'm writing y square plus z square, and 0 y and z. This is electric field. And similarly the magnetic field, if you combine all those three components, if you want to write down in terms of the individual components, although there is no need to write it in this way because all that we have learned that these are nothing but the components of the field tensor. But again and again I'm writing these separately because we are interested in knowing the field components, because we are more comfortable in to think in terms of electric field and magnetic field, because those are physical things that we know which are sourced by current and the charge distribution. So we feel comfortable about thinking in electric field and magnetic field, right? Any tensor like object like the field tensor, I mean that's an abstract quantity, and we are saying that these things are nothing but the components of that quantity. That is mathematically correct, but each time you think just that those are the different components of field tensor, what are the physical meaning of it, because we can easily relate the electric field and magnetic field to physical things, right? These are physical things which you can feel and sense. So that's why we are writing them. Otherwise there is no need, there is no compulsion that you have to do this. Gamma lambda v divided by twice pi epsilon 0, there will be c square. Again y and y prime are same, so I am writing y square plus z square, and here you see 0, this is z, this is y. Now you see depending on which axis, along which axis the wire is lying, and the motion of the prime frame, these results will change, right? If I move along the z axis, right? Let us take at least one example, and I will not solve, just I'm solving another example, right, for you. You can but you guys should try it, right? Because if you are moving along different direction, what will be the result? At least try a few, right, so that you become confident. So let us solve another problem where I will consider a frame which is moving, say, along the say minus z axis. Let us make it slightly more different. So minus z, say this is moving along the minus z axis, then what will be the field tensor or the electric field and magnetic field in this frame? So that is our next goal. We want to figure out that, right? So let us do that. So if you are moving along the z axis, so what is the corresponding Lorentz transformation matrix? I think it's trivial, but again, I mean, for the sake of completeness, I am just doing this, right? So, what is the Lorentz transformation? The mu nu won't change, right? If I change the problem in such a way that where the lab frame is fixed, lab frame is same, where the wire is lying, right? It is the wire lying along the x-axis. Of course, this can lie along any other direction, or I can have two wires, one along the x-axis, and I can make the things complicated. You don't have to go to any textbook. You can formulate new problem yourself, right? If I take three wires, say, or two wires of different charge density, one lying along the x-axis, another lying along the z-axis, and then ask you to calculate the field tensor, you should be able to calculate it, right? That is what I expect from you, right? I do not expect to solve you very complicated. If you go to Jackson's book, there are many complicated problems. But the thing is that unless you can solve some simple problems which are based on a fundamental concept, I mean, it is very unusual to solve, I mean, very difficult problems. So these are very simple problems. So let us consider this example where I am assuming that the moving frame, say this is the prime frame, x prime, y prime, and z prime. This time, say the y, yeah, okay, the frame is moving, say, along the, yeah, I have drawn it correctly. So say this is the minus z axis. The frame is moving along this direction, right? So v is minus v z cap, right? It is moving along the minus z axis. If it is moving along the minus z axis, then what should be the electric field and magnetic field in that frame? So this is the laboratory frame, this is the moving frame, and I want to calculate the electric field and magnetic field in this frame. So for that, again, you don't need to worry at all, because you know it's a tensor, and we have learned how to transform this tensor from one inertial frame to other. Once you know that, you should be able to calculate the electric field and magnetic field, because they are nothing but the six distinct components of the field tensor only. Okay, so f mu nu is already known to us. What is f mu nu in the lab frame? That we have already written earlier. So 0, 0, it has y and z component, ui by c, ez by c, 0, 0, no, 0, 0, minus ui by c, minus ez by c, and rest are all 0, right? This is the f mu nu in the laboratory frame. We want to calculate what is f mu nu prime in this frame, right? In this frame. That is our exercise. Again, you see, this, while solving this problem, the most important steps involved in this exercise are writing down f mu nu correctly in a given frame. So that is your first exercise. You first have to write down, identify the components, what are the electric field and magnetic field for a particular given problem, and then write down the field tensor correctly. That is the first step. The second step involved in this exercise is to write down the transformation matrix correctly. If you do these two steps in a correct way, a result will be correct, right? So in this case, since the frame is moving along the minus z axis, so what should be the Lorentz transformation matrix in this case? If I ask you, what is lambda mu nu in this case? What is lambda mu nu? So lambda mu nu, it is moving along the z axis, right? So that means gamma should be here. It will be all the time, to be 0, gamma 0, 0, and then plus or minus
Plus beta.
plus beta gamma, right? Correct. Plus beta gamma, not minus beta gamma, right? Because it is moving on the minus z axis. 0, 1, 0, 0, and then 0, 0, 1, 0. This will be again plus beta gamma, right? Plus and minus will make a lot of difference. That should be careful about. Right? This is the lambda mu nu, and the rest is easy, right? You just have to multiply three matrices. That's a trivial exercise. You write down this gamma 0, 0, beta gamma, then 0, 1, 0, 0, and then you write 0, 0, 1, 0, beta gamma, 0, 0, gamma, and then you have this matrix 0, 0, ey by c, ez by c, 0, minus ey by c, minus ez by c. Rest of the components are 0. So multiplication becomes much easier. Into gamma 0, 0, beta gamma 0, 1, 0, 0, 0, 0, 1, 0, beta gamma 0, 0, gamma. Right. So okay, I'm not again doing this multiplication. All of you can do this. It's a straightforward multiplication. Lots of zeros, right? So I'm just writing the result, right? So I'm leaving it to you. So this is a home assignment. You can do it yourself, or I will do. You can find it in my notes, which I will provide. So here, if you multiply all these three matrices, you will land up with this result: 0, 0, gamma ey by c, Ez by c. No, this time you see there is no gamma Ez by c, Ez by c. So results could be quite different depending on the direction of motion. So don't just try to memorize any result. Gamma ey by c, this will be minus Ez by c, minus Ez by c. This will be again 0, this will be 0, this will be 0, 0, 0 minus beta gamma ui by c, ui by c, 0, this will be beta gamma, of course, y minus plus 0, 0, right? So you can easily figure out what are the components of electric field and magnetic field in this case, right? You see there is no x component, so the ex prime will be 0. What is ui prime? Ui prime is gamma ey, right? What is Ez prime? Ez prime doesn't change, because you have learned that the electric field and magnetic field along the direction of motion doesn't change. Ez prime will be Ez. That is the case here, right? And what is the magnetic field component? Bx prime. You see what is, which one is x component? If you remember, bx prime is this one, right? Beta gamma ey by c with a minus sign here, right? This is bx prime minus beta gamma ey by c. This is bx prime, this is minus bx prime, right? This is bx prime minus beta gamma ey by c. And you see all the other special components are 0. So by prime is 0, bz prime is 0. So I just showed you two examples in this class, and you should be able to solve similar problem. That is my expectation, right? So as you have seen that it is very easy to formulate many such problems, right, based on this basic idea, right? Right, I can provide many scenario where the electric field and magnetic field could have different direction, and then you should be able to write down the field tensor in that frame. And remember that it is not necessary to write the f mu nu only in the lab frame. It could be in any frame, because all inertial frames are equivalent. You should be prepared to write down the field tensor in any inertial frame, and once you write that, you should be able to transform it to any given inertial frame. For that, you have to find out the proper transformation matrix. That's all. Okay, so how much time we have? Okay, still 10 minutes. Maybe I can try to solve another problem. Okay, let me just give one such example where I will write the field tensor in the prime frame, not in this frame, right? So let us do another solve another problem where I will write the tensor in the prime frame, not in the laboratory frame. Okay, so let me first just describe the problem. So the problem is the following. So we have two large parallel plates, right, separated by a distance d. So the plates are lying on the, say, xz axis, and they are separated along the y axis. Okay, imagine this picture where the two large plates which are lying on the xz plane. So these two planes, the plates, are separated by a distance d along the y axis, and these two plates are moving along the x axis with velocity, say, v. Now imagine the upper plate is charged with a charge density, say, plus sigma, and the lower plate is charged with a charge density minus sigma, right? And then you have to find out. So okay, let me draw the picture that will make things slightly clear. So this is the laboratory frame, and in the laboratory frame we do not know f mu nu, right? We want to figure out what is the electric field and magnetic field produced by this system in the laboratory frame. This is laboratory frame, and we are considering the system in the moving frame, right, where the plates are static. In the moving frame, which is moving along the x axis, which is called S prime frame, this is x prime, this is y prime, this is z prime, and we have two such plates, right? This is upper plate and, say, another plate. This, the separation between them is, say, d in this prime frame, and the upper plate is charged with, say, positive charge density plus sigma, lower is charged with charge density minus sigma, right? So it's like a parallel plate capacitor with nothing in between them. This is an empty space, no dielectric like that. Of course, I can insert a dielectric, right? So this should be able to solve such problem. I can also insert two dielectric, right? Anyway, in this problem there is no dielectric. It's an empty space, right? Now what I'm asking is to calculate the electric field and magnetic field in the lab frame, right? This is the lab frame. You have to calculate the electric field and magnetic field in the lab frame. So to do that, again, I told you that just write down the tensor in the frame where the system is at rest. So the plates are in the rest in the moving frame, right? It's an own co-moving frame or the rest frame of the plates. And remember, this charge density are, as I told you, that charge density and current density, they are the components of 4 current density, 4 vector, right? So you should also be aware of the fact that charge density is not invariant, that changes from one frame to other. So in this problem, when I say that the upper plate is charged with charge density plus sigma, what I am trying to say that this charge density is the charge density of the plate where it is at rest, right? In the rest frame, the charge density of the upper plate is plus sigma and the charge density of the lower plate is minus sigma. So there will be an electric field generated by this pointing towards this, right? Electric field. So that electric field that you know from your electrostatic course, so what should be the electric field, right? Some sigma by epsilon 0, right? So what would be the electric field in this frame? If I ask you, we want to first write down the field tensor in the prime frame, then only we will be able to transform it to this frame. So what are the components? Tell me, what is ex prime? What is ex prime? Anybody?
0,
Right. What is ui prime?
0, 0 হবে। না, না, 0
Again,
minus
হবে।
sigma
and what is z prime? Z prime will be pointing towards minus z axis, right? I have already drawn the arrows, minus. So minus, you are right, minus sigma by epsilon 0. This is the electric field z component. And since the plates are not moving, they are at fixed location in the moving frame, so we can straight away write the magnetic fields are 0. There are no magnetic field, right, in the prime frame. But remember that these plates are moving in this frame, so it is not necessary to have zero magnetic field. Of course, there will be non-zero magnetic field that you want to figure out. So let us write down then f. Bolo.
স্যার প্লেট গুলো তো এক্সজেড প্লেনে আছে না?
xz প্লেনে আছে।
তাহলে স্যার ওয়াই কম্পোনেন্টটা পাওয়া যাবে না?
আমি কি লিখলাম? Okay, right. I mean, yeah, you are right. What I am, this is in this example, maybe I have drawn the axis wrong, right? No problem. I mean, what he is saying, right. I mean, now দেখে এটা x y z একই ভাবে লিখলাম, তাই ও ঠিকই বলেছে যে y কম্পোনেন্টটা এখানে নন জিরো হবে, মাইনাস সিগমা বাই এপসাইলন জিরো, রাইট? অফ কোর্স, ইউ আর রাইট। সো কাটবো নাকি এটা এক্সিসটা চেঞ্জ করে দেবো? কাটাকাটি না করে এবং এটা চেঞ্জ করে দেওয়াই ভালো, তাই তো? এটাকে বরং এক্স করে দিই। তাহলে কি করতে হবে? দাঁড়াও, এটাকে এক্স করতে হবে, এটাকে ওয়াই করতে হবে, এটাকে জেড করতে হবে। না, ফাইন, ইট ডাজন্ট, ঠিক আছে, এইটাকে এক্স ওয়াই জেড করে দেবো। আচ্ছা, লিখে ফেলেছি যখন থাকছে না, ওই যখন বলছে, আচ্ছা থাক, ওই যখন বলছে এটাকে এটাই করে দিই, মাইনাস অফ সিগমা বাই এপসাইলন 0, রাইট? এটাকে তাহলে এটা 0 হয়ে যাবে। হোয়াট হি সেইং ইজ কারেক্ট, রাইট? যে ডাইরেকশনে কোনো ইলেকট্রিক ফিল্ড নেই, রাইট? তো আমার আইডিয়াটা পেয়ে গেলে এই প্রবলেমগুলো সলভ করার কিছু ব্যাপার না, রাইট? ইউ হ্যাভ টু জাস্ট মাইন্ডফুল যে কোন কম্পোনেন্টটা কোন দিকে। আমার মতো এখানে অন্যমনস্ক হয়ে গেলে হবে না, রাইট? এটা আমার অন্যমনস্কতার রেজাল্ট। ওকে, সো যেটা তোমাদের পরীক্ষাতেও হতে পারে। সো ইউ শুড বি কেয়ারফুল, রাইট? যে এফ মিনিটটা ঠিকভাবে লিখতে হবে, ল্যামডা মিনিটটা ঠিকভাবে লিখতে হবে, তাহলেই তোমার কারেক্ট রেজাল্ট পেয়ে যাবে। তাহলে দেখো এখানে কি হলো, শুধু ইউআইটা রয়েছে, ইজেডটা নেই, রাইট? ইজেড থাকলে ইজেড থাকতো, এখানে ইজেড নেই। আমি এই প্রবলেমটাকে 5 রকম ভাবে ঘুরিয়ে দিতে পারি, তাই না? একই রকম ভাবে আমি বলি প্লেটগুলো অ্যালাইন্ড হচ্ছে গিয়ে এক্স ওয়াই প্লেনে, separated by some distance d along the other axis, right? So the same problem can be reoriented or slightly changed. And you have so you cannot really, I mean, you don't need to memorize anything, you just have to write down the tensor correctly and then you solve it, right? So এই পার্টিকুলার এক্সাম্পলটাতে আমি যেটা বলতে চাইছিলাম যে এখানে তার মানে তুমি তাহলে এবার লিখে ফেলো কি হচ্ছে, তার মানে 0, এটা 0 হবে, তাই তো? এটা 0 হবে, তারপরটা কি হবে? ex 0, ইউআইটা রয়েছে, তাহলে সেটা কত হবে? মাইনাস অফ সিগমা বাই এপসাইলন 0 সি, ই বাই সি হয়। আর এটা কি হবে? এটা মাইনাস, কোনো এখানে মাইনাস রয়েছে, এটা কি হবে? এটা 0 হবে। তেমনি এদিকে কি হবে? হোয়াট আর দ্য আদার কম্পোনেন্টস? স্পেস টাইম কম্পোনেন্ট, টাইম স্পেস কম্পোনেন্ট 0, দিস উইল বি প্লাস সিগমা বাই এপসাইলন 0 সি, দিস উইল বি অ্যাগেন 0, অ্যান্ড এগুলো আর লেখার দরকার নেই, এগুলো সব 0 হবে। অল দ্য স্পেস কম্পোনেন্টস আর 0 ইন দিস ফ্রেম, রাইট? আচ্ছা, তাহলে আমি এটা করছি না, এখানে ম্যাট্রিক্স মাল্টিপ্লিকেশন বেশি কিছু নেই অ্যাকচুয়ালি। আমি জাস্ট তোমাদের বলতে চাইছি যে এই ধরনের প্রবলেম তোমরা কিছু নিজেরা প্র্যাকটিস করো। এখন তুমি যে বলো কোনো আলাদা করে মানে বেসিক জিনিসটা বুঝে গেলে আর কোনো প্রবলেম হওয়ার কথা নয়, রাইট? আমি এটা যদি ধরো আমি যেটা বলছিলাম, ওই যেটা ভুল করে রেখেছিলাম, সেটা যদি হতো তখন এটা 0 হতো, যে ডাইরেকশন হলে তখন এটা মাইনাস সিগমা বাই এপসাইলন 0 সি হতো, এটা 0 হতো, right? And the why I am going to this example is basically যে আমরা f মিউটা অন্য প্রাইম ফ্রেমে ক্যালকুলেট করছি, তাহলে প্রাইম ফ্রেম থেকে যদি ওই ফ্রেমে যায় তাহলে এখানে আমাকে কারেক্ট ভাবে লিখতে হবে। এটা যদি এক্স অ্যাক্সিস বরাবর মুভ করে, আর আমি যদি প্রাইম ফ্রেম থেকে ইফ আই ওয়ান্ট টু সুইচ টু দ্য ল্যাব ফ্রেম, what should be the corresponding f mu nu prime? I want to calculate f mu nu, right? Not f mu nu prime, f mu nu। তাহলে f mu nu এখানে f mu nu থাকলো, f mu nu prime এখানে তোমাকে lambda lambda mu alpha, right? Beta alpha nu beta gamma beta nu mu alpha and beta nu। তাহলে এই জিনিসটা তোমাকে ঠিক করে লিখতে হবে। তাহলে এইটা কি হবে, এটা কি হবে এখানে বলো তোমার, এটা বলতে পারলে তাহলে করতে পারবে। এটা তো লেখা হয়ে গেল। হোয়াট উইল বি দিস ম্যাট্রিক্স, হোয়াট উইল বি ল্যামডা মিউ ইন দিস কেস, কি হবে এটা?
gamma beta gamma 0 0 b
গামা, কারেক্ট, গামা বিটা গামা 0 0 বিটা গামা গামা 0। এইখানে মিস্টেকটা হয় যে কোন ফ্রেম থেকে কোন ফ্রেম। তাহলে এই ফ্রেমকে যদি দেখো আমি যেটা বলেছি আগে যে কোন দেয়ার ইজ নো স্পেশাল ইনার্শিয়াল ফ্রেম, ইফ আই এম ইন দিস ফ্রেম then that frame is moving opposite to the I mean plus x axis, right? According to an observer who is at rest in this frame, these plates are at rest and the lab frame is actually moving along the minus x axis, right? So from the perspective of an observer in the prime frame, the lab frame is actually moving along the minus x axis. So what you have to do, you have to put minus b in place of b. That's why it become gamma plus beta gamma, not minus beta gamma. And 0 0 1 0 0 0 0 1. So you again, it's a trivial exercise, put the gamma matrix and multiply the f mu nu matrix with that and you will get the correct result. But again, I mean the most important steps that I mean, because I have seen this many times from my experience in teaching this course for last I think more than, I think I've taught this course for more than 6 years now. So and this it's a common mistake. Lots of students who understand this clearly but even then make a mistake in the exam because they do not write the either transformation matrix correctly or f mu nu correctly. So if either of them are wrong or both of them are wrong, then obviously you will get a wrong result. So these two matrix has to be written correctly, then only you can get the correct value and direction of the electric field and magnetic field in the problem, whatever is the problem. So right, so again you see I'm because this is repetitive, because once you get the idea, it is not, even if I give you say 10 problems, I mean the idea is same. Suppose okay, I'm telling you another problem. So suppose I have an electromagnetic wave, right? Till now we are dealing with say charged wire or say charged plate, or I can have also a, say current carrying wire. Okay, suppose I have a current carrying wire lying along the y-axis, and I ask you to calculate f mu nu in a given frame and then calculate the electric field and magnetic field in some other frame. So all that you have to do is that you have to write down the field components in that frame. Again, suppose if I ask you, suppose that there is an electromagnetic wave which is propagating say along the say z axis in a given frame, inertial frame. It could be lab frame, it could be some moving frame, whatever it may be, because you know that the frequency changes due to Doppler effect, and also the wave vector changes because frequency and wave vectors are nothing but the four components of the four wave vector that we have discussed earlier. But here we are concerned about electric field and magnetic field, right, in this problem. So suppose I give you an electromagnetic wave which is propagating along say the z direction. So you can easily write down the equation for electric field for that wave, right? You have learned it in your previous semester. Course how to write down the electric field along the z axis. And once you are able to write down the electric field, you can also write down the magnetic field because it is known to you, because electric field and magnetic field are orthogonal to each other, right? And the wave vector, electric field and magnetic field, so you know the relationship between magnetic field and electric field. Once you write down the electric field, you can be also write down the magnetic field associated with the electromagnetic wave. And once you know the electric field and magnetic field associated with the electromagnetic wave, you can write down the field tensor associated with the electromagnetic field of that wave, right? And once you do that, you can calculate the electric field and magnetic field of that same electromagnetic wave in any other inertial frame, right? You may have to also, suppose I ask you calculate f mu nu, f mu nu, that once you write down f mu nu, you will be able to calculate f mu nu, f mu nu. So what is the invariant quantity? That we already know. For electromagnetic wave, it is always E square minus C square B square. For some other problems, also depending on the value of E and B, you will end up with some positive or negative result, right? So this sort of problem I expect you to solve, right? So practice such problems. So I'm not going to stress this further, because these problems are identical. So once you have the idea and you solve a couple of problems, you should be confident about solving such problems. Okay, so any question? No question. So if there is no question, then I should assume either all of you are understanding whatever I am saying, or none of you are understanding whatever I am saying. So either it is too good or too bad. Anyway. No question? Okay, fine. Then we shall continue our discussion. Okay, one more thing I forgot to mention. One more thing, because from tomorrow onwards in the department we have several meetings. So tomorrow there is a board of strategy meeting, and then after that on 27th and 28th there is a full day meeting for the final selection of PhD students. So there will be interview on 28th, that is on the Friday. 27 and 28 both. সো আমাদের শুক্রবারের ক্লাসটা হবে না, ওই দিন সারাদিনই ইন্টারভিউ চলবে। আমাদের নেক্সট ক্লাস হবে পরের উইকে মঙ্গলবার, ঠিক আছে? যারা অলরেডি লিভ করে গেছে তাদেরকে বলে দিও, আমি আর আলাদা করে পোস্ট করছি না হোয়াটসঅ্যাপে।